These are kind of special types of matrices that we come across in various applications in physics. So we have talked about diagonal matrices, triangular matrices, symmetric matrices in yesterday's class. So symmetric matrices, A is symmetric if A transpose is same as A. And is called antisymmetric. A transpose is equal to minus A. Then A is antisymmetric. And we are using orthogonal matrices are defined as A transpose is equal to A transpose A is equal to identity. This implies that A transpose is A inverse. It implies A transpose is A inverse. You can immediately show that determinant of K is plus minus 1. You cannot have any other determinant. If A is orthogonal matrix, determinant of A is plus 1 or minus 1. This you can show immediately because determinant of A transpose is same as determinant of A transpose is same as determinant of A. So determinant of A transpose is determinant of A square, which is determinant of I. Determinant of I is 1. So A square is 1 means A is plus minus 1. So that's the proof. Now, let me just fill here. If you consider a set of all orthogonal matrix, the determinant of A is equal to plus 1, it becomes a group. Even though I did not define group, but I hope I said vector space V plus is an abelian group. So, if you consider a set of all orthogonal matrices, the determinant plus 1, it forms a group. So, such a group is called SO2. SO2 group is set up of orthogonal matrices. We call it special orthogonal matrices because determinant is plus 1. And if it is plus 1 or minus 1, then we have what is called orthogonal groups. These are called continuous groups. So continuous compact groups. So SO2 is a set of all orthogonal matrices with determinant 1, and O2 is set of all orthogonal matrices. So the determinant is plus 1 or minus 1. Hermitian matrices are defined as the adjoint of A is equal to A. Adjoint of A is equal to A. Adjoint of the matrix is its transpose conjugate. So it is exactly like transpose, but if the matrix is a complex matrix, then you have to take conjugate. So adjoint is complex conjugate. There's also one more thing that I can prove here in the orthogonal case. Let me come back to this a bit later. If you have a vector and if orthogonal matrix is acting as vector, vector will change into some other vector. So let me use, so today I will try to use Dirac notation in most of my discussion so that you will be familiar with using that notation. Suppose if I have a vector x and then orthogonal matrix is acting on x, I will get a vector y. Okay? Now, this implies if I consider the inner product of y with itself, this is equal to inner product of x and A transpose A into x. This is product of y and this is f vector y. But you know A transpose A is identical. This is equal to x. So orthogonal transformation will leave the norm invariant. Norm of the vectors will be left invariant by the orthogonal transformation.
So in general, like scalar product, you have to use square dagger.
If it is a complex vector, but right now this x is a real vector. Okay, so if it is a real matrix, A dagger is A transpose because there is no conjugate. Conjugate is same. Okay, so orthogonal transformation will leave the norm of the real vectors invariant. In fact, you will see that the rotation matrices are all orthogonal transformation. Okay, so rotation matrices are orthogonal. Now, Hermitian matrices, A dagger is equal to A. And if A dagger is equal to minus A, then A is anti skew Hermitian. Anti-Hermitian or skew Hermitian. Okay, so this is as far as Hermitian operators are concerned. The definition of Hermitian operator. Unitary operator is like orthogonal. A dagger is equal to A dagger A is equal to identity. That means A inverse is a joint A dagger. So here you can say that determinant of A what can we say about the determinant of A? Determinant of A is the determinant of A dagger. Determinant of A dagger will be determinant of A transpose conjugate. So determinant of A transpose is same as determinant of A. So it is transpose of the determinant of A. It is a conjugate of determinant of A. So you can say that mod A square, this modulus of the determinant of A square should be 1. That means your determinant can be a complex number with a unit magnitude. Okay? So you can say determinant is equal to e power time e or something. You can only say that determinant has unit magnitude. Or you can write so you cannot say anything about this theta. What you can say is modulus of determinant of A is equal to 1. That's all. Magnitude of the determinant of A is equal to 1. And similarly, you can write what is called, if you take a complex vector A acting on X is equal to Y, then inner product of Y is equal to X A dagger A X, but since this is 1, so a joint, the unitary matrices will leave the norm of the vectors, complex vectors invariant. Then talk about normal matrices. Normal matrices are defined that A adjoint of A is same as adjoint of A. Any matrix which satisfies this relation is called a normal matrix. That is, A is normal if A commutes with its adjoint. A is normal if A commutes with its adjoint A diagonal. So you can see unitary, Hermitian, orthogonal, symmetric, all these are normal matrices. If you take Hermitian operator, if you take unitary, A diagonal is identity, A diagonal is identity. So this is satisfied. If you take Hermitian, this is A square, this is satisfied. So other things are real counterparts of this. So it is actually a superclass of all this. If some matrix is any one of these, it is this. But the converse need not be true. You can find still some normal matrices which are not Hermitian, which are not unitary, which are not symmetric, which are not. So it's a larger class. Normal matrix is a larger class of and
So in the real case, you wrote for a unitary matrix, determinant modulus of determinant of A is equal to 1.
yeah.
It's actually modulus of determinant A square is equal to 1.
Yeah, so what happens is, let me put it this way, if I say determinant of A dagger is equal to determinant of A into determinant of A dagger, correct? So which is equal to determinant of A into determinant of A transpose conjugate. So which is equal to determinant of A into determinant of A transpose conjugate. But determinant of A transpose is same as determinant of A. So I will have determinant of A into determinant of A transpose. So this will be equal to modulus of determinant of A square is equal to this. This is what it is. Correct? So that means what this will be equal to. So we have determinant of A mod square is equal to 1. Correct? Determinant of mod square is equal to 1. Oh, so you are saying, yeah, so determinant of mod square is equal to 1. So modulus of determinant of A is also equal to 1, right?
Yes. So minus 1.
No, in general I will say determinant of A is equal to, this is modulus, mod square is 1, so 1 into e power I theta. So this is complex number with modulus 1, correct? So this is modulus.
Suppose you take plus or minus a raised to a theta.
Plus or minus? See, this plus 1 or minus 1 comes because of this theta only, right? If theta equal to 0 it is plus, if theta equal to pi it is minus. So when I put e power I theta, I have all possibilities, not only plus and minus. Okay, so that is about the normal matrices, normal matrices. And then we have a category called positive definite matrices. Positive definite matrix is defined in the following fashion, that A is positive definite, or sometimes it is called as positive if Okay, this quantity is positive, is greater than or equal to 0 for all x belonging to the vector space. If A is acting on the vector space, if you construct this quantity, take any vector and construct this quantity, you should get only positive, not 0. So it should be non-negative. A is positive matrix if this condition is satisfied. One can construct a positive matrix from a vector. We have talked about, suppose if we have